I'm going to start by asking everybody to help me out a little bit. I don't understand why this happens. I start class with the knowledge that it's scheduled to end at 5:05, and then something happens during class, and I think as I'm getting closer to 4:50 that, oh my gosh, class is almost over, I better finish up. And I think I've done that twice already, and I don't like to waste class time, so if it looks like I'm doing that, feel free to be like, we actually have a few more minutes if you want to do some more stuff, okay? I want to give you your money's worth, so I'm going to start out by stating my intentions to actually use our class time today. We're turning in assignment 1 today, and it's due by 11:59. I think I've already gotten some submissions on Canvas. Does anybody have any questions they would like to ask about it?
I have a question number 5, just
Yeah.
kind of how to get it started.
Mm-hmm. So 5, oh yeah, okay, yeah. So we want to use the axioms, meaning like those properties of a Boolean algebra. So that was like commutativity, associative, distributive properties, the complement laws, right? And what the identity laws. So we want to prove that AB plus A naught B is B. So it's a Boolean algebra proof, so we usually do this by, like with a string of equations. I usually start with the side that's got the most stuff going on. So if you start with this side, I'm going to resist any temptation I might have to say equals B right there, because that would just be stating that it's true, right? I know that there's going to be some stuff I do, and at the end I'm hoping that I can say, oh, the whole thing is equal to B. Anything we can do on that side, any opportunities, any axioms we can use.
The distributive.
So the distributive, and what would we get there?
It's A plus A prime times B plus B.
So I don't think it would be this.
I got
Just times what?
B times A plus.
Yeah, just times B. Right, because distributive is sort of like, if I distributed, right, it's the distributive property in reverse. So the distributive property says if I have this fact, I guess for lack of a better term, a factor of B, I could send it through over addition. So I just see this as the result of having distributed that B, and I undo it. Yeah.
Okay.
From there, we should be like 1 or 2 steps away, right? So maybe look at the complement laws and see what you can do with this. Mm-hmm. Other questions?
Number 3.
Number 3. Oops. Oh, yeah, okay, all right. So we're finding a counterexample. So number 3 is easier than you think. You don't have to write a proof for these. You can certainly be as explanatory as you like. But it's really, once you find the sets that'll work, all you have to do is say, this thing is true, but this thing is not in these sets. And so the statement can't be true generally. So in the first part, in part A, I think we talked about did we talk about part A on Monday?
Yeah.
So maybe I'll just talk about part B a little bit this time. So part B says if A is a subset of B and A intersects C is empty, then B intersect C is empty. So I'm telling you at the outset that this statement, this if-then, does not hold. This is false. And if something is false, we ought to be able to find an instance where, that it doesn't hold. So if you're trying to show that an if-then is false, what you want to do is come up with an example of actual sets, like list out, curly braces, list out the elements. This is in A, this is in B, this is in C. And you want the if statement to be true. So you want to make sure that A is contained in B. You want to make sure that A and C do not overlap at all, but that the then statement is false. So you want to make sure that B and C do overlap somewhere. And I often just start by, picking a set for A. It doesn't have to be large. Maybe it's like 1, 2, 3, 4, 5. Doesn't even have to be that big. But when I pick B, B has to have all those same elements, right? Maybe more, right? If A is contained in B, I've got to start with the elements of A and then maybe add some more stuff if I want to. That will make sure that this part is true. And then I simply need to find another set C. And I need to pick C so that it does not overlap with A at all. No elements in common, but it has to have at least one element in common with B. That's basically what we want to do. Does that help with that one?
Yep, thank you.
Okay. Proving that something is false is usually a lot easier than proving something's true. To show that something's false, you just have to find an instance where it fails. To show that something's true, you have to show it's always true, and that's where we write these nice long proofs and stuff. Other questions? Okay. All right, then let's start talking about relations. Well, last time, or one of the last times, we talked about sets. We defined the Cartesian product of two sets, and we said, if I have a couple of sets, the Cartesian product of A and B is just the set of all ordered pairs. So the Cartesian product, the order matters. With A cross B, the first coordinate has to be from A, the second coordinate has to be from B. And a relation from A to B, or a relation between A and B, is simply a subset of the Cartesian product. Really, you could think of, when we looked at functions in calculus and pre-calculus and algebra, and we said, okay, there was going to be this correspondence that some input value corresponds to an output value, and it had to satisfy a special condition that every input could only correspond to one output. With a relation, we just say, suppose there are no rules. Anything can be related to anything. It's a way of picking coordinates, right? Like pairs, like A is related to B, but basically anything goes. So if we are given a couple of sets, A and B here, then their Cartesian product, so A is 1, 2, 3, B contains the elements R, S, so the Cartesian product has those 6 ordered pairs. We want to know, initially it says write down a relation R between A and B. So first of all, we usually use capital letters to denote a relation. So I'm just going to take any old collection of those ordered pairs that we wrote down, or that are listed there for A cross B. Maybe I pick 1R, and I could pick 2R, and I could pick, 3S and 2S. Nothing special about those 4 that I picked. I just picked some collection, some subset of that Cartesian product. There are lots of possibilities. Then it says, how many different relations are there? How many different relations could I define? So a relation is any subset of the Cartesian product. How many subsets are there of this Cartesian product, and how do I know? Say that again?
2 to the 4th?
Not 2 to the 4th. How big is the Cartesian product?
That's R, right? R is the Cartesian product?
No, R was the relation that I just sort of picked out of thin air.
Oh.
And I picked it by taking a subset of the Cartesian product, A cross B. So the Cartesian product is this right here.
2 to the 6.
2 to the 6. Yeah, was your mic on?
No.
Okay.
It's 2 to the 6.
Yes, 2 to the 6. So when we answer how many relations are there, what we're really asking is, what is the size of the power set of A cross B? Right? How many subsets? And that is 2 to the 6, or 64. So there are 64, that includes the empty set. That includes the relation where we say nothing's related to anything, right? That's a relation. It's not a very interesting one, but it is one. If we have a relation from a set to itself, I'm going to scroll up here back to the definition. If I have a relation from a set to itself, so it's a subset of, let's say, A cross A, then we say that that is just a relation on A. When we list that an element is related to another, we might do so by saying, oh, this ordered pair is in the relation. But we might also just say A, R, B, using the same capital R. Like if I'm using R for the relation, I would say A, R, B. If I use capital S for the relation, I would say A, S, B. So those are just two different types of notation we might run into. The set of real numbers, if I consider this following relation on the real numbers. So I'm just looking at coordinates where the first coordinate and the second coordinate are both real numbers, essentially points in the plane that we know and love. We could define a relation like this. It's going to be the set of all ordered pairs, such that x squared plus y squared equals 4. What does that look like? Like if we just, here's R cross R, right? That's the real line. Here's the real numbers by the real numbers. So we can plot points. What is one pair, xy pair, that's in that relation? X squared plus y squared equals 4.
Would it be?
Oh, you might have it.
Root 2 for each value.
Okay, so we could use root 2 and root 2. Okay. Hold on. Root 2 is like 1.414. So like there. Yep. Anything else?
That'd be true for negative root 2 as well.
Yeah. In fact, I think we'll get some in each quadrant. So like negative root 2, positive root 2. I'm trying to make it accurate, and that's going to be the death of me. Negative root 2, and then negative root 2, negative root 2. So we got some symmetry going on here. Root 2, negative root 2. There's I would say 4 others that are kind of, they're maybe a little bit obvious. Like what if it was, well, certainly there are numbers we could find where, like, say x is 0. What would y be? 2, right? 0 is related to 2, and 2 is related to 0. 0 is related to -2, -2 is related to 0. So we get these points here. Maybe this is starting to take shape a little bit. Say that again. Turn on your mic.
It's a circle.
It's a circle centered at the origin of radius 2. Yep. Great. We use some of the same terms when we talk about relations as we do with functions. So if we have a relation from A to B, we say that that the elements of A are the domain of that relation. And the codomain would be the set B. The range would be all the values of B that actually are related to by some element in A, right? So like maybe I have a relation between A and B, but maybe not everything in B ends up being a second coordinate. All the things that end up being that second coordinate, those collection of elements from B, that's the range. So if we could identify the domain and range from the examples in the last two that we just did. Let's see. In example 116, the domain is just all the set of all the first coordinates. So 1, 2, and 3. I guess we got everything in A. And in fact, we also got everything in B, showed up as being second coordinates. So the domain was all of A and the range was all of B. Let's see. So that relation was 1R, 2R, 3S, 2S, and the domain was the set 1, 2, 3, which is all of A, and the range was the set RS, which is all of B. That doesn't always happen. The domain is not always all of A. The range is not always all of B. In fact, if we look at the example, the last one, example 117, I'm going to go back and take a look at that. Since we kind of sketched it and we're able to kind of visualize what this relation looks like, what is the domain? What are all the possible first coordinates?
0, -root of 2.
Say that again.
0, -root of 2, and root of 2.
Those are included, but you're missing infinitely many more elements.
Would you want to define them in terms of the y?
Well, if I'm looking at the first coordinates, I just want to define them. Like, what are the x values? If we look at, I would really just look at the circle that we drew, right? Everything on that circle is going to be, are the coordinates, the point. Those are the points that we would be including in that relation.
So it's all values of x between -root 2 and positive root 2.
Closer.
It's all values of x between -2 and 2.
-2 and 2, right? I'm going to include all the ones that show up. So I don't want to stop at -root 2 because, like, I would leave out -2, 0, for example. So the domain is basically these real numbers right here, right? All those x values, all those x coordinates, or all those x values end up being coordinates in this relation. What about the range?
Same, but on the y-axis.
Same, but on the y-axis, yeah. So there's symmetry to the circle. So if I were to write this out, I would just say, rather than list the set twice, I might just say the domain is equal to the range. And so instead of making a separate statement for x and y, I'm just going to say that it's a set of all t, I'm just going to pick another variable in the reals such that -2 is less than or equal to t is less than or equal to 2. So here's an example where the range was not all real numbers, the domain was not all real numbers, right? It can be some subset of those sets. So if we think of a relation as a collection of ordered pairs, we can get an inverse relation just by taking each ordered pair and flipping it, right? For any relation we have, there is an inverse relation, and it's a relation from B to A instead, and we just flip all of those ordered pairs that we had. And we use we denote it with a superscript 1 for an inverse, and it's defined pretty simply. If AB is in R, then BA is in R inverse. If I have a couple of relations, say I have a relation R from A to B, and I have another relation S from B to C, then I can find their composition. I can kind of mush those two relations together and get a relation from A to C. So you basically, finding a composition is trying to find a way to leapfrog your way from one set to another with the elements of B that are in the range of one relation and also in the domain of the other relation, kind of connecting them together. So that's what this means when it says there is an element B in B such that AB is in R and BC is in S, right? Where these are the same. So there might be lots of stuff that you miss, lots of elements of A that are not related to elements of C because there's not a connecting element in B that'll get you there. When we denote, when we write out a composition, we use this little circle here. So S composed with R. And if we're finding S composed with R, look at the order here. R goes from A to B and S goes from B to C. So if I think about like my sets A, B, and C, I have to go from A to B via R first and B to C via S. So when we write out, notice the order in which we wrote out this composition. S composed with R. R is the one on the inside is evaluated first. If we have a relation R from A to B and a relation S from B to C, then there is no R composed with S. Because if I apply S first, I go from B to C, and R doesn't go from C to anywhere, right? R goes from A to B. So the order in which you do a composition is important. Let's do an example. So R and S are a set of positive integers defined by, or R and S are relations on the positive integers, which means they're relations from the positive integers to the positive integers. What S does is it takes any positive integer and relates it to the integer that's 2 more than itself. So for example, 2 is related to 4 and 13 is related to 15. R is the relation that takes some positive integer and squares it. So 7 is related to 49, and I don't know, 16 is related to 256? Okay, yeah, good. So we're going to find the two compositions. And when we say find the compositions, I mean, can we write them out in like the form of a formula like we did here? So S composed with R. Note that because both of these are relations from the positive integers to itself, both compositions are defined. Because once I get from, when I apply one relation, I'm still in the positive integers, and I can apply the other relation to it. So S composed with R. So the first thing we're going to do is use the R relation here. So I'm going to take an element X, It's going to be related to. The first thing I'm going to do is square it. And then what do we do after that? If I apply the S relation.
You add 2.
Yeah, we just add 2. So this is going to relate x to x squared plus 2. R composed with S, if I take a positive integer x, this time I'm gonna apply the S relation first. What will that relate x to? So if I apply S first, it'll add 2, and then we apply R. So what are we gonna do to that?
Whole square.
Yeah, just square the whole thing. One thing we can observe in this example is that relation composition is not commutative. So if we did just a couple of examples here to see how this, like concrete examples. Let's apply, let's look at the S composed with R. And let's just see how this works. So first, if we take the integer 3, what is that related to in the R relation? We apply R first. 9, because we're going to square it. And now look at 9, and I'm going to apply the S relation to 9. So what is 9 related to in the S relation?
$11.
11, because the S relation says just add 2. I'm going to scroll back for just a moment. Up here, this is, we said, the way we defined this composition, you know, T consists of the ordered pairs AC, such that there's some element B that connects, you know, A goes to B and then B goes to C. There has to be a connecting element between the two. So 3, 9 is in R and 9, 11 is in S. Here we see 9 connecting the elements 3 and 11 together. So that means that 3 is related to 11 in the composition S composed with R. If I take, just to kind of drive home the point that this relation composition is not commutative, suppose I take the same integer 3, and first I apply S. So if I apply the S relation first, then I'm going to add 2 first. So that's 3 is related to 5. And now I'm going to apply the R relation to 5. R tells me to square it, so 5 is related to 25. That's in the R relation. And now we can see that 5 is sort of an element of B, or you know, an element in the middle. Of course, for us, that set is still the positive integers. But that ties 3 to 25 in the composition R composed with S. The last thing I'll say about compositions, for now at least, is just that it is associative. So if you happen to have 3 relations, which will require you to have like 4 sets so that the relations are compatible, like one relation goes from A to B, the other one has to pick up from B to C, and so on, that the function composition is associative. So it doesn't matter how you group them. The order does matter. The order in which the relations appear, right? TSR, I'm not changing that up, but just the order, and you know, how you group them doesn't matter. Let's look at some interesting properties that a relation on a set A can have. So right now, we are specifically talking about a relation from a set to itself. So a relation may have some several or none of these properties. We're going to be particularly interested in special types of relations that have some collection of these properties. But we say that a relation on R is reflexive if A is related to A for all elements of A. Another way to say that is A is related to A, if you like that notation better, instead of the ordered pair. It's reflexive if everything is related to itself. That seems aptly named. Now, a relation could be reflexive, or a relation could not be reflexive. For a relation to just be not reflexive, it just means there's at least some element not related to itself, right? The for all doesn't carry, doesn't hold. It's also possible for a relation to be super extra not reflexive. We call that anti-reflexive. And that means if a relation is anti-reflexive, it means that nothing is related to itself. So this means that if A is related to B, like an ordered pair, A, B being in the relation, means that A cannot be equal to B. So nothing is related to itself. Up here, everything is related to itself. You could think of these two properties as being kind of polar opposites. They're not negations of each other, but polar opposites. Everything related to itself, nothing related to itself. There's lots of relations that have something in between. So a relation doesn't have to be one or the other. A relation is symmetric. Let's see, I'm going to start this off, and then if you use the word, what does the word symmetric kind of mean to you, I bet you can guess how it's going to end. So if I have an ordered pair A, B in the relation, that implies, if it's symmetric, if we have symmetry, what do you think we can do? What do you think this means? Guesses are fine.
Would they be the same?
They're the same.
Well,
Yeah.
no, not that they have to be the same. That would be kind of forcing a reflexiveness, sort of, which will actually come up with anti-symmetry. But yeah, what did you say?
BA.
Yeah, BA is going to be, and we can flip it. I don't know why I put anti-symmetric after transitive on the list, but we're going to do anti-symmetric first. So symmetric means anytime you have an ordered pair in, then its flipped ordered pair is also in there. You have to have it. It's possible for a relation to not be symmetric if you're just missing one of the flipped ordered pairs. That's all that's required, is that you just don't have every single one of them. Something is anti-symmetric if there is no symmetry at all. Meaning, that means that if, like for all A and B in our set A, if you had a case where it looked like you had some symmetry, so say the ordered pair AB is in the relation and the ordered pair BA is in the relation, if that were the case, then in fact A would be equal to B. Like when you think you have a case of symmetry, like a little bit of symmetry, as it turns out, it's just reflexive. So anti-symmetry is no symmetry at all allowed. Symmetric is all symmetry. Like anytime you have an ordered pair, you can flip it. And now, finally, the transitive property says, here for transitive, we need to grab three elements. So whenever A is related to B and B is related to C, then what do you suppose we'll have in there?
A is related to C.
A is related to C. Yeah, it's kind of like a leapfrog property. Almost like you're kind of composing the relation with itself, but you already have those elements. So we have these properties. I said in the beginning, when we were looking at reflexive and anti-reflexive, it's possible for a relation to be reflexive. It's possible for it to be anti-reflexive. It doesn't have to be one or the other. It could be neither, all right? But it can't be both. You can't be reflexive and anti-reflexive at the same time. You can't be symmetric and anti-symmetric at the same time. But you don't have to be either. So we're going to get a little practice. Here's a set. So we have the set of integers from 1 through 6. And they've defined a relation just by listing out these ordered pairs. And we want to just check for each of these properties. Okay. Is it reflexive? And what are we looking for?
It's reflexive, isn't it?
It is, and what tells us that it's reflexive?
Because A is 1 through 6, and the y coordinate is also 1 through 6.
Well, so we see 1 through 6 represented
Oh, wait,
as outputs.
I kind of cut off the last half in my brain,
Okay.
like the last half of the R.
What is it that we're looking for in the set of ordered pairs they give us in the relation?
I guess we're looking to see if for each unique element in A, if the first element of an ordered pair is that element, then the other should be as well.
Right. We're looking. It's not that anytime we have an element. Well, let me see if I understand what you're saying correctly. You're saying. So well, actually, do this. Based on that, do you think this is reflexive?
So I see the first 6 ordered pairs
Uh-huh.
where you see 1, 1, and 2, 2, etc.
Yeah.
Until the last element, and so I can conclude it's reflexive by the way I understand it.
Yeah. No, you're right. We have all doubles. That's basically what we're looking for. Something's reflexive if everything in the set is related to itself. It could also be related to other things, right? 1 can be related to 4, and 1 can be related to whatever, as long as I also have 1 related to itself, and 2 related to itself, and 3 related to itself. So this gets a yes. It gets a yes.
If we were missing one of those first 6 elements, it would knock it.
Correct. Yeah. Yep. It wouldn't be anti-reflexive either, right? Anti-reflexive means you can't have any doubles at all. Reflexive means you have to have all the doubles. So there are lots of relations that are neither of these. So we've concluded this is reflexive. So that means it can't be anti-reflexive, so that's going to get a no. What about symmetric? What are we looking for there?
Mirror images of every element.
Yeah. And so what do we think?
Yes.
Yes, so we could just do a quick, we could do an exhaustive check without too much time because the set's not too big, but here's 1, 2, and 2, 1. Here's 1, 4, and 4, 1. Here's 2, 4, and 4, 2. Here's 3, 5, and 5, 3. And then the first 6 are the, symmetric of themselves, right? Because they're just the doubles. So symmetric gets a yes. And if it's symmetric, it can't be anti-symmetric. Well, that gets a no. And then the last one, transitive, is probably the hardest one to check, just because it's the hardest one to check in a case like this, where they just give us a list of ordered pairs, because we kind of have to check all of the possible ones, but it's not too huge. I don't think it'll take that long. So like, look at this. 1, 2 is in there, and 2, 1 is in there. So if it were transitive, I'd need to have 1, 1, and we do, right? 1, 2 is in there, and 2, 4 is in there. So I'd need to have, 1, 4, right? So it's the inner elements, right? The second coordinate of the first one and the first coordinate of the second one, that ties them together, and then I have to check for, are the outer coordinates related to each other? So I need 1, 4 to be in here, and it is. You could keep going. 1, 2 is in there, and I think I already checked all those. 1, 4 is in there, and 4, 1 is in there, so then again we'd be looking for 1, 1. It doesn't take that long. It's a little bit tedious, but if you check, we do in fact have all of the all of those pairs that we need. So this is transitive.
I'm a little confused.
Yes.
About the final little. Oh, no, I'm looking at the wrong thing. Never mind. I was looking at the anti-symmetric.
Oh, okay. When you are given just a list of ordered pairs, I suppose it's not too bad, but if this list of ordered pairs was substantially longer, we'd have a harder time with it. A lot of the relations that we work with won't be given by explicitly listing the ordered pairs. They'll be given by just describing what it means for one element to be related to another. On the next page, we have one such relation. Here we're defining a relation on the positive integers by saying x is related to y if y is a multiple of x. So x is related to y if y is a multiple of x, so we could say that if y is a multiple of x, that means y is equal to k times x for some integer k. And then this says which properties does R have? We couldn't possibly list all the ordered pairs even if we wanted to. The set is an infinite set. So even if we really liked the tedious process of checking every ordered pair possible, that's not an option here. So we're going to check, let's go through in order. Is it reflexive? So what we want to know is x related to x for all x, for every positive integer x? Well, what do you think? If we bring this back to how this relation is defined, really what we want to answer is x a multiple of x?
Isn't it not
Yeah, K is one,
because
yes.
Y?
I don't know what either of you said.
If K is 1, then yeah.
Oh yeah, right. Okay. So if we think about, certainly every integer is a multiple of itself. It's 1 times itself. So this will get a yes. Does that make sense? Like 5 is a multiple of 5, right? It's 1 times 5. If it's reflexive, it can't be anti-reflexive. So this gets a yes. And that means we don't have to check. We know it's not anti-reflexive. Is it symmetric? So when a relation has a property, we want to construct, this is a really short argument, but we were able to construct an argument, yes, because x is equal to 1 times x. That covers every single integer, positive integer, right? I didn't use an example to show it. It can be helpful to think by example to kind of get us started, but whatever we write down, if we want to say yes, it has that property, well, whatever we write down has to apply for all infinitely many positive integers. What if something, well, let's see, let's think about symmetry here. Do we think this relation is symmetric? And it can be helpful to think examples first, right? So can somebody tell me an integer that's related to another positive integer with this relation? Basically I'm just saying, can you give me an integer and then some multiple of that integer?
Like 4 and 2.
4 and 2. So 4 is a multiple of 2. So you're saying that if 4 is a multiple of 2, let's be specific. Are you saying that 4, 2 is in the relation or 2, 4 is in the relation?
I don't know.
Okay, so let's go back up. So when I'm doing problems with relations, I always bring everything back to how the relation's defined in the wording. So we say x, they tell us x, y is in the relation. X is related to y if y is a multiple of x. So the number here, the second coordinate has to be a multiple of the first coordinate. So that means which one of these is in the relation?
2, 4.
And is 4, 2 in the relation?
No,
No. What do we think about symmetry?
not symmetric.
It's not symmetric. Okay, so I've got good news for everybody. I'm only erasing this to kind of make room to write the same thing over again in a more organized fashion. So we're saying no. Now we don't need to write an argument that holds for all integers. In order to show that a relation's not symmetric, we need only find one instance where the relation's not symmetric. So all we just say is no, because 2, 4 is in the relation. But 4, 2 is not in the relation. Done. If it were symmetric, I'd be able to flip them for any ordered pair. Yeah.
Is transitivity, transitiveness?
Transitivity, yep.
Is that like reflexiveness or symmetry in the sense that it has to be completely transitive or only semi-transitive in order to be qualified as transitive?
I don't understand. Something has to be completely reflexive to be reflexive and completely symmetric to be symmetric. So there's not a semi-reflexive or semi-symmetric.
Oh, okay. Sorry.
Right?
Yeah, I guess.
Because this got a no right here, right? We found one instance where it didn't hold, so it's just not symmetric. There might be some. Yeah, go ahead.
It's not necessarily anti-symmetric either, right?
Not necessarily, but let's check. It doesn't have to be one or the other. It could be neither.
I guess my question is, does every element of the set have to be transitive?
An element is not transitive. The relation itself is transitive. An element, like transitive is not a term that applies to an actual element. It applies to the relation itself.
Okay, that's what I mean. But
Okay.
yeah, I'll just let you continue. Maybe the answer will.
Yeah, when we're going to talk about anti-symmetric first, and then when we talk about transitive, maybe we'll answer your question more fully. So the next one, this next one is anti-symmetric. Is it anti-symmetric? Okay. Anti-symmetry means you can't have any symmetry at all. Anti-symmetry, let's go back to the definition. A relation is anti-symmetric if for all elements in your set, if you have an instance of symmetry, right? If I suppose that it is the case that A, B is in the relation and B, A is in the relation, then as it turns out, A and B are the same element. That it's just a case of an element being related to itself. So, can there be no symmetry at all? Is it possible? Think of when it would be possible to reverse the coordinates for this relation, where we say x and y are related. What's that?
Would be 1-1.
Is your mic on?
It was.
Okay, good. 1-1.
Yeah, I said
So
1-1.
1-1. Yep. Any others? Because we can reverse that.
Zero, zero.
Well, not 0-0 because only because we've defined this relation on the positive integers, and
Sure.
0 is not positive. But there's others
Anything where 1 is half of it.
like. So 1 is related to 3, right? 3 is a multiple of 1. So you're saying anything where, so I'll give you 1 is related,
Never mind.
okay, because we can't reverse those ones, right? We have 1-1, what else? There's lots others.
Any square?
Like 5 and 25?
No, that doesn't work either.
I'll tell you, the only things I can think of that I could reverse would be things like 1-1, 2-2, 3-3. Right? I mean, if this multiple relationship, right? Like y is a multiple of x. If x is also a multiple of y, I would think that multiple would have to be 1, right? Like 1 times something. So I'm going to go ahead and say I think this is anti-symmetric because I think the only time we can actually reverse and still have that multiple relation hold is when it's the same, an integer being related to itself, right? Because if you look at 2, 4, and as soon as you reverse it, it's not an integer multiple anymore, right? It's a fraction of it. So we're going to write a convincing argument that this is anti-symmetric. And remember, if we're showing that a relation does have a property, that means that what we write has to hold for all infinitely many positive integers. So I'm going to start by saying let's let m and n be positive integers. And let's suppose that m is related to n and n is related to m. Like, we're going to suppose that we have found an instance of symmetry in this relation. If this is anti-symmetric, we're hoping to be able to conclude that n and m are the same integer, are the same positive integer. So, let's see what this gets us. If m and n is in the relation, right? If m is related to n, that means n is a multiple of m. So I can write n is equal to, I don't know, k times m for some integer k. And in fact, it's not just an integer, but it's got to be a positive. If m and n are positive integers, k has to be a positive integer, in fact. So I'll just add that little note here. Also, since n is related to m, that's the other thing, right, that we're supposing. Then n is some integer, I'll call this one j, times, whoops, I'll reverse that. M is a multiple of n, so m is some integer, I'll call it j, times n for some positive integer k. J. This is what we get just by using how the relation's defined, right? We suppose m is related to n, and that gets us this first line, right? So if n's a multiple of m, I can write n as k times n. If n is related to m, then m's a multiple of n, so I can write m is equal to j times n for some positive integer k. So now, let's observe some stuff. N is equal to k times m. Right? We get that right from right here. I'm just using that equation. M, however, is j times n. So I'm gonna make that substitution here. So this is k times j times n. So I've got a product of 3 positive integers. Now I'm gonna group those two. I want to look at I want to see this as kj times n. Now look at this. This n on this side of the equation is kj times n. So what does k times j have to equal? 1. K times j has to be 1. And k and j are both positive integers. So what do k and j have to both be? 1. That's the only way. I'm going to multiply 2 positive integers and get 1. The only way that happens is if they're both 1. So if k and j are both equal to 1, we'll bring this back to these two equations, and we find that, in fact, n must be equal to m. So we started out saying, suppose m is related to n, and n is related to m, and we were able to conclude that n and m must be the same. And that means that this relation is in fact anti-symmetric. The only instances of symmetry we're going to find are the doubles, where an element's related to itself. Are there questions on how we worked out this argument that we made? When I'm working with a relation that's been defined, trying to figure stuff out about it, I often start with examples. Like, I just want to get a feel for what this relation is. It's really important to note that a counterexample can be used to show that a relation does not have a property, right? We found an example to show something was not symmetric. But it was really important that we wrote like kind of a more rigorous argument that applied for all infinitely many elements of the positive integers to show that this relation had this property. The next property, I think it's the last one that we have here, is to check and see, is it transitive?
Did we go over the observe line again before we get to this?
Yeah. Oh, yeah. So the observe line. So I started with the integer n, and I used this equation that we already knew, right? If m was related to n, we knew that n was a multiple of m, so n was k times m for some positive integer k. So I just wrote that here. Then I took, I have m involved here in that expression, that product. The other thing we knew was that because n was related to m, then m was equal to j times n. So I took j times n and just substituted it. Oh boy, that looks awful. Hold on. Yeah. So here's m is j times n, and I substituted that in for m here. So that's why I have j times n at the end of that equation. Does that make sense so far? Okay.
Yeah, I guess I don't really see where the k comes in with the j times n.
Oh, because of this right here. We said suppose m is related to n. And what that gets us is this line right here, this equation that's outlined, that's highlighted in blue. If m is related to n, that means n has to be a multiple of m. And if you're a multiple of m, then you're some positive integer times m. So we were able to say n must be k times m for some integer k. That's just by the definition of the relation, how the relation is defined. So then I took that equation and just repeated it down here. Is that any better?
Yeah.
I still I have a question on observed
Mm-hmm.
line. So if you replace m with jn,
Mm-hmm.
and then you divide it both sides with n, right? And that
Right,
what
yeah.
you-
I mean, I don't know. I wouldn't say we necessarily divided, but you could think of it that way. It's just that I didn't really think of it as having divided, but I'm gonna zoom in on one part of this equation. Okay, so I'm making lots of marks here, but I'm gonna.
Just like control, zoom in, just like.
So I have three sides to this equation. I have the n in the beginning, in the middle I have km, and then this third side, kj times n, after I make that substitution. So I'm going to look at just the left, the n, and the other side, the very left and the very right sides. If I look at those, we have n equals kjn, right? I'm just ignoring the middle part. The middle part, I really have the middle part just to get me to this equation, right? I'm just using that substitution to get me here. So whatever k times j is, it's some integer. N is equal to k times j times n. The only way that happens is if the product k times j is equal to 1. Does that help?
Okay.
Yeah, okay.
Yes.
Cool. And if k and j are both positive integers, then of course they have to both be 1. Look, it's 4:52, and I'm remembering that our class doesn't end until 5:05. Just want to point that out. Small victories. I'm going to take them where I can get them. So the last property is showing that it's transitive, because this relation, in fact, is transitive. If I kind of think by example first, like 2 is related to 4, right? Because 4 is a multiple of 2. Anything that 4 is related to is going to be a multiple of 4. And anything that's a multiple of 4 has to be a multiple of 2, right? Because 4's got that factor of 2. So, so this relation is transitive. We need to, of course, not just think of an example of transitivity. We need to show that it's transitive. We need to construct an argument that works for all infinitely many positive integers. So with transitivity, it's sort of like that leapfrog, right? If A is related to B and B is related to C, then A is related to C. So we actually need to grab 3 arbitrary elements and assume that we have those relations going on. So let's suppose that A is related to B and that B is related to C. We're going to show, right, if we have these two, if these two pairs of elements are in the relation, we're going to show that A is related to C. Okay. The only thing we have to go on is how the relation is defined. So if A is related to B, then what does that give us? What does it mean to say that A is related to B for this relation?
B is a multiple of A.
That B is a multiple of A? So what can we write? Yeah. So B is some integer k times A. And in fact, we know that k is a positive integer because A and B are positive integers. And we also have B is related to C. Right? That was the other thing we assumed. So what does that let us write?
C equals J times B.
Yeah, C is some integer, say J times B. Okay, now we want to show that A is related to C. So I'm going to start with C. If A is related to C, like which is what I want to show, I'm hoping that we can write C as some multiple of A, right? So I'm going to start with C. So let's observe.
Can we do this like the last one where you swap, where B equals K times A, you just swap that into the E?
Yeah,
Yeah.
yeah. So C is J. So I'm going to start with C. That's J times B. And Nia, why don't you describe what you're just talking about?
From our anti-symmetric one, we re-swapped the.
We kind of substituted
We substituted the M,
Mhm.
and N equals K times M.
because we had another equation.
Right.
So what in this case, what do you want to substitute?
The B, since we have the equation for the B.
Right. So you're saying this equation up here, if B is K times A, then we can plug that in for B right here. Great. Let's do that. So this is J times K times A. So let's look at this equation. Again, I've got like a three-sided equation. I'm going to look at the very left and the very right. Let's pull out that equation. So we know that C is equal to JK times A. What do we know about J? J is a positive integer. What do we know about K? Also a positive integer. And what do I get if I multiply two positive integers? A positive integer. So JK is a positive integer. And what does that mean? What does that allow us to conclude? I've been able to write C as a positive integer times A. What does that mean?
That C is a multiple of A.
Yeah, C is a multiple of A. And we're just about at the end of this. We're like standing 2 inches from the finish line right now on this. What do we want to be able to say? In fact, we even stated our intentions at the beginning of this transitive proof. What are we going to show?
That B is also a multiple of that.
We knew that to begin with. That B is a multiple of A?
Yeah.
Yeah,
and
that was
part
part of our
mine,
assumption.
Like we already stated it.
Yeah, that was part of our assumption. So we have...
That R is transitive.
It's transitive. In fact, you know, the one thing I'm going to say before is that we have this ordered pair. Like, right up here at the beginning, we will show AC is in the relation. So let's just say it, right? So yeah, R is transitive.
I'm okay right now, but if I actually try to do it,
So make sure, okay, so Nia just said, I feel like I'm okay right now, but when I actually try to do it, right, it's going to be hard. It is going to be hard. We're learning new skills, right? We're learning that we have to keep going back to the proof. It's not like just solving an equation. It's not as algorithmic as a lot of the math we tend to learn. You know, like there's like a real pattern to it. I mean, if you do enough of these relation type proof problems, you start to recognize some patterns, but it's not nearly as algorithmic as, oh, take derivatives or solve for x or something. So I'm going to just take this opportunity right now to plug those practice exercises. There's problems there and worked out solutions in the back. So if you get stuck, you see how I did it. Like sometimes even just reading out how I did a problem, that counts as like thinking about these problems, like having a go at them, saying, oh yeah, okay, I could see like maybe some patterns emerging, and you could feel like you're in a slightly better shape when you start the assignment. So I guess this is a good breaking point. Not that we're at our breaking point. A break point in the material. We'll pick up and finish out. There's a bit more to do with relations, so we're going to finish out this relations. Look at partial orderings and equivalence relations. Both partial ordering and equivalence relations are just special kinds of relations. So we'll pick up where we left off on today's Wednesday. On Monday, I'll be in Randolph that day. Take a look at assignment 2. You can start, the sooner you start struggling with it, the sooner you can start asking questions and having fun. Enjoy your weekend, everybody, and I'll see you Monday.